Okay, so hopefully you picked up some ideas for how to build your own list based off of seeing the client side view of it. But now I want to actually show you the data structure and I want to show you the API to the list that I built. And I'll do that, I think, without biasing you too much to do it one way or the other, because there are still a lot of different possibilities. And I mainly want to make sure you understand, don't waste a lot of time, and have a few ideas to build off of. So let me share my screen again, and this time I'll be showing the list.h header file that goes with the list implementation that I just used in the test code. Okay, so the first thing to notice, as now we're looking at the list.h header file, is this is exactly the same, except I'm actually doing a singly connected list, just for simplicity. The example that we did in class with integers was a doubly connected list. So all I have is a pointer to next. And the other thing to realize is this is now void star. So this is the trick that I use to gain generality. And I imagine many of you will. There are other ways one could approach it as well, depending on how much you want the compiler to do and how much you want to be able to specify at runtime. Okay, but I'm saying this list stores a pointer to any blob of data, and that blob of data can represent absolutely any type that anyone wants to define. So it's perfectly general. Okay, the price you pay is you have to do some casting, and you have to deal all in pointers in your source code. So other solutions are possible. Now, what does my list look like? Well, it looks a lot like the integer list in class, except I've added a few things. And the few things I've added are critical. So the size of the list hasn't changed. It's just the number of elements in the list for convenience. And I'll jump down to the bottom. There's still the head and the tail of the list haven't changed. It's always important to store the tail to make append an order constant time operation. I have three functions, and these are the three pointers to functions I showed you in the client code. Okay, so this first function, remember this funny syntax for a pointer to function. So this is a pointer to function that takes a pointer to void and returns an int. And what this function is going to do is for the particular data structure that you're using in a particular usage of the list, it's going to say how to free an element of that data structure. And similarly for toString, it's saying how for the particular type that you are using with the list, what the textual representation is going to look like of an instance of that object. And the function is going to return a char star because the source code is going to just print to the screen whatever this gives back. But if you don't say that, there's no way for the source code to know how to represent one of your objects that you're using with the list. I also include a match function. The match function says if any two elements of the list are equal. And it's the same thing. It's easy to say if two integers are equal with nothing special. But if you have 2 points or 2 pairs, you have to say what the criterion for equality is. Otherwise, there's no way for the source code to know. So it's going to use all of these functions to augment its own functionality and achieve generality. Okay, and I'm not going to use this in the list implementation. So why do I have it here? Well, it turns out I can build other data structures by essentially subclassing in a sort of cheap ANSI C way off of a list. And that subclass, I might do something like a set implementation. Remember, a set does not allow duplicates. And so I would need to check when I put a new element in a set if the element existed already, because I can't duplicate it. So I might want to inherit that function and this quote unquote subclass, okay? And so we just all hide this under the abstraction list in the way I do it. Like I told you in class, you could create an abstraction, which is a pointer to a list. It all depends on what you want the user to see and really your own style and your own taste. Okay, so what does the interface look like? Well, I told you I think of this as sort of order constant time and order n functions. List init is what it is. It just caches pointers to the method, the function pointers that are going to be needed by the source code. List destroy is going to just loop over all elements of the list and free each element. List insert next is an order constant time function because it's low level interface. It requires the element prior to the one that you want to delete in order to be able to successfully operate. And same with list rem next. Okay, so those are possibly building blocks to your own list implementation, or they could be things you expose to the user, depending on who you imagine your user to be. Okay, and then the sort of nicer part to the interface, list print, list add, are index-based operations, or list append, which applies to the last index, and then element at, which is index-based. So these are nicer, right? But you're hiding from the user the fact that you're traversing list elements in order to execute these functions. And so if performance is at a premium, you have to be very careful as the user to know the data structure well enough to know what it's doing so that you're not writing inefficient code. But what's the stuff at the bottom? Well, I mean, these are like functions. They're called macros in C, and they look like functions. But what actually happens is anytime that you write list size list, the compiler just replaces it with list.size, right? So why would you do that? Well, first, you don't want the user to necessarily know the internal details of the opaque list type. So you don't want them dereferencing the structure as sort of a software engineering point. So you want to think of it like a accessor method in an object-oriented language. Well, why don't you write an accessor method? Well, you could, and you probably would these days. In the old days, you don't want to pay the cost of a function jump. It would be considered inefficient to have the code, the object code for that operation exist elsewhere and to have to do a jump and return. So if you do it this way, it just inlines it in the code, which means it repeats it many times, but it's more efficient to execute. So this is a bit of an archaic strategy, but you know, those of us who were around in the old days are used to it and it feels good. Okay, so you can define all of these as macros, or you can define them as functions. And in fact, C has a keyword inline now, which gives a hint to the compiler to inline rather than to do a jump to some object code that's stored in other places. But that's the entire interface. Okay, and I hope by seeing the interface, you get insight into how you could do this in a general way. And so what I want to do in the next segment is look at a little bit of the source code to demystify some of the vague comments I made about the implementation or about how the toString and destroy methods are used. And I think once I do that, you'll have enough where you can begin your own implementation, hopefully using some of these ideas and some ideas of your own.